We're going to get started here. This is homework 1 for process dynamics and controls. My name is Connor Bush, and I will be walking us through homework 1. So beginning with part A, we are looking to derive the differential equation that describes a dynamical liquid level in response of a conical tank. This conical tank has a total height of 8 meters. The top radius is 5 meters with the bottom radius of 1 meter. The drain at the very bottom of the tank has a cross-sectional area of 0.01 meters cubed. Initially, we are looking at a steady state with the flow rate coming in at 0.1 meters cubed per second of liquid flowing in. And we need to simulate the liquid level of the tank for 5,000 seconds when we look at increasing the flow rate coming in by 20%. So I'm going to move over to my iPad here. I have a small schematic of what we are looking at. Excuse me. We have a conical tank. The flow rate coming in is 0.1 meters cubed per second. The radius at the top is 5 meters. The radius at the bottom is 1. Cross-sectional area of the hole is 0.01 meters squared. We call this AH. And then the height, the total height is 8 meters. We call this H total. So we are going to ultimately need an expression for dH dt, which is the change of height with respect to time. But first we need to look at finding that from dV dt, the change in volume with respect to time. We know that the change in volume with respect to time is equal to the difference in the flow rates coming in and the difference of the flow rate going in minus the flow rate going out. We know also that volume equals some area times the height. So we are looking at a changing cross-sectional area of the conical tank here. I just expressed that at some height. We are looking at a cross-sectional area here. So that will be changing with respect to height. So we can say the change in volume with respect to height multiplied by the change in height with respect to time is equal to dV dt. And then also, obviously, this is equal to the difference in the flow rates. We're going to call this portion here AC, which we will derive an expression for momentarily. But for now, we're going to simplify this expression. We know what Qin is. We are given that it is 0.1 meters cubed per second. And we divide by the cross-sectional area at a given height. We do not know what Q out is, so we need to determine an expression for that. We are going to need to use energy balance in this case. We are looking initially at steady state. So we're going to say at the very top of this tank that there's only gravitational potential energy that we have to worry about, and that kinetic energy, the small changes in height are negligible, so we don't have to factor that in. But at the very bottom, when height is 0, that we are looking completely at just kinetic energy. So if we put that into an expression, we're saying the initial potential energy equals the final potential kinetic energy. So acceleration due to gravity times any height h is equal to the velocity leaving squared divided by 2. And then if we solve for velocity, we get this expression. And then we also know that the flow rate is also equal to some cross-sectional area. We know the cross-sectional area of the hole at the bottom, we call that AH, is the flow rate out is equal to the flow rate, the cross-sectional area of the hole multiplied by the velocity leaving. So we can substitute that into this expression here for Q out. And this is what we are we're left with. So this is our expression for dHdt. Now we need to look at two more things. So we are going to be looking at an ODE solver in Python. So we're going to need an initial guess for the height. So to get that, we know that initially we are at steady state, so that dHdt is 0. And with that, we know that dHdt is equal to the flow rate going in minus flow rate going out over AC. But in this case, when we are at steady state, this is all equal to 0. So if we set this equal to 0, we're left with Qn naught. This is the initial flow rate of the liquid coming in while we are at that steady state. This is equal to the initial flow rate going out. And then we have this expression here for the out input. The H value is, this one here is going to be H naught, as the rest are just parameters and are constants. So AH, which is not changing, multiplied by radical 2G. I'm going to separate out H naught, so it's easy to solve for. And then if we solve for H naught, we are left with the initial flow rate going in divided by cross-sectional area of the hole multiplied by radical 2G, this entire expression squared. So this is our initial guess for the height that we are going to be using in the ODE solver. Now, like I said, that we need to determine an expression for AC. We know that AC is essentially, it is the cross-section area, and the shape of it is a circle. So we know that the area of a circle is expressed as pi r squared. And we know that the radius is changing. So if we look at the relationship between the radius and the height, at height 0, we are looking at our bottom, the radius of the bottom of the conical tank. And then when we are at the total height, we are at the very top of the tank. So we can see that this is a linear expression. So if we write out the equation for a line, r equals, that's our dependent variable. We have to have our slope. So the top radius subtracted by the bottom radius divided by the total height minus 0, since at the bottom height is 0. Multiply this by our independent variable h. And then our y-intercept is our bottom. So we will plug this in to our well, to get the expression for the cross-sectional area AC. So now we will go into Colaboratory and begin illustrating all of this data within Python.
All right, so now that we are in Colaboratory, we need to initialize 3 libraries. We're going to import NumPy. We are going to import our subplot. Subplot library from Plotly. And then also the solve initial value problem from SciPy. Okay, great. So now we need to initialize the parameters that are given to us. So we can start with G, gravitation, or acceleration due to gravity, meters per second squared, are the units. We know that the initial flow rate coming in is 0.1 meters. I'm just looking at my iPad with everything that I used previously. So that is 0.1 meters cubed per second, units for that. We know that the radius at the top is 5 meters. The radius at the bottom is 1 meter. The total height is 8 meters. We know that we're going to need to use an initial guess, so we're going to include h naught here, and that is from the equation we derived here. So that is equal to the initial flow rate in divided by the cross-sectional area of the hole, which we'll have to initialize above, multiplied by the square root of 2g. And then all of this will be squared. Area, cross-sectional area of the hole at the bottom is equal to 0.01. This is in square meters. We're going to make all of these floats just for the purpose of calculations. And then we know that the time that we want is around 5,000 seconds, which we can always change, and we will do that here. And then I want to include a sort of increase factor as a variable, just to make it easier to change and have that as a variable. So now next what we're going to need to do is make a function for the cross-sectional area, and that will be a function of the height, total height, and then the top and bottom radii. So I will type that out here. And then, as I was saying, that the radius is changing, which obviously affects the area. So we're going to need to include the area of the line because there's a linear relationship between the radius and the height. So we will have that here. So this is our slope. Change in the top and bottom radii divided by the total height minus 0, so we can omit the 0. This will be multiplied by our independent variable h, and then we're adding the y-intercept, which is the bottom radius. We're going to add parentheses here to ensure that everything comes out calculated correctly, and then we are going to return the actual area, and the area of a circle is just pi times the radius squared. So next, we will also need to make a function for dH/dt, which is kind of our function of interest. We just need time and height as the parameters. We are changing the flow rate coming in, so we can express that as the initial flow rate in multiplied by this increase factor f. And then we will need to store AC as a sort of variable itself, and we can do that by calling the function above with all of these listed parameters. I'm just going to copy and paste. And then we want to return an array of values. So here we are going to use the dH/dt equation that we derived here. So I will type that in now. That is the flow rate coming in minus the flow rate coming out. We expressed that as the cross-sectional area of the hole multiplied by the square root of 2 times g times h. And then all of this is divided by the cross-sectional area AC. Now we want to use the solve IVP, or the initial value problem, that we imported from SciPy. We need to call the function dH/dt. The time span will be from 0 to t end, and then our initial guess for height will be h naught. we need to also set the dense output to true, so we have a continuous result, so we can actually pull from that. So now this is all of the sort of equations that we need so we can get into the plotting. So our x-axis will be called t-plot, and that is just going to be a series of points from 0 to t, and we'll have 100 of them. And then our y-axis will be the height. So from this result variable, we'll pull the solution using the points from t-plot beginning at 0. And then now we can plot this using Plotly. So we'll initialize that we're making a subplot, and then we're going to add a scatter plot. Our x-axis will be t-plot, and then our y will be heights, and then we're going to update the layout. I have a few parameters here. We're going to include a title for the graph. I'll just call it tank level. The x-axis title will be called time in seconds. Our y-axis title will be height in meters. And then to adjust the dimensions of the plot, we're going to specify that the width will be around 600 pixels and then the height will be around 400. So let's see how this looks. So obviously you can see that height as a function of time, there's this curve. We're beginning at a steady state and it's trying to get to work its way to the next steady state. So if we increase the time here by a factor of 10, we can see that it does in fact reach the second steady state. So this kind of covers everything that we need to do for part A of homework 1. We are simulating how the tank level changes when we increase the flow rate coming in by a factor of 20%. So now we will get into part B.